Hi, everyone, and welcome to Module 7, Lesson 2. In this lesson, we're going to look at the nature of gases. We're going to look at vapor pressure, and we're going to look at phase changes, which we should be familiar with already, and look at phase diagrams. So we're going to start off here with the kinetic molecular theory, which is used to describe an ideal gas. There is a difference between what is known as a real gas and an ideal gas. Real gases are the gases in the atmosphere, the ones that are around us. But when we talk about gases, we think of them as ideal gases because basically it just makes it easier for us to do all the calculations that we need. So the kinetic molecular theory states that particles in a gas are considered to be small, hard spheres with an insignificant volume. We know that isn't true when we talk about a real gas, but we're again talking about an ideal gas. The motion of the particles in a gas is rapid, constant, and random. We are probably aware of that one. All collisions between particles in a gas are perfectly elastic. So what that means, if they come, they're going to hit each other and they're just going to bounce off in opposite directions without losing any energy or speed. Okay, so you can think about it like a car accident. A perfectly elastic collision would be, oh, you like hit bumpers and bump away. Okay, nothing really happens. Whereas inelastic would be they get all crumpled together. Then we have particles are neither attracted or repelled by others. Again, we know real gases will be attracted and repelled by each other. But when we talk about these ideal gases, we consider them to not be attracted or repelled. And then kinetic motion is proportional to the temperature in Kelvin. So if you heat them up, you're going to speed them up. So the motion will be faster as we increase the temperature in Kelvin. Atmospheric pressure results from a collision of atoms and molecules in air with objects, and a barometer is used to measure atmospheric pressure. You can see this is an original barometer where you've got a pool of mercury in basically a tube with a vacuum in it. And as basically the atmosphere is pushing down on the mercury, it goes up into the tube. And one of the units for pressure that we are going to talk about is actually millimeters of mercury, where they literally measured how many millimeters of mercury it went up in this column. The SI unit for pressure is Pascal, but we're going to use one of three standard units at STP. We're going to either use atmospheres, millimeters of mercury, or kPa, which is kilopascals. Now, 1 atmosphere is the pressure at STP, so standard temperature and pressure, 1 atmosphere. So these are just standard pressures. So it's either 1 atmosphere, 760 millimeters of mercury, or 101.3 kPa. They're all the same, and these are what you can use to do your conversion. So let's say I have 1.2 atmospheres, and I want to know how many millimeters of mercury. Well, I know in 1 atmosphere, there's 760 millimeters of mercury. So we can just do a little dimensional analysis. We'll be left with the unit that we want, and that's how we would do it. Pressure, we can think about as force exerted over an area. If you want to think about a high heel versus a sneaker, which would hurt more to get stomped on, it's going to be a high heel, because the high heel, the point is so small, and you've got all that force exerted over a much smaller area, which makes the pressure higher. When we're talking about pressure for gases, we're basically talking about collisions. The more collisions is like pressure. So when a molecule, a gas molecule, a particle collides with the side of its container, that is what we read as pressure. So in the atmosphere, it's when they collide with each other or other objects in the air. So when we think about pressure, we want to be thinking about collisions. Vapor pressure is a measure of force exerted by a gas above a liquid. Okay, so it's the pressure of gas above a liquid. So in a system at constant vapor pressure, a dynamic equilibrium exists between the vapor and the liquid. The system is in equilibrium because the rate of evaporation of liquid equals the rate of condensation of vapor. An increase in the temperature of the contained liquid increases the vapor pressure. So what this means is that if I have a container that's sealed, there is an equilibrium happening. So what's happening is the liquid is evaporating at the same rate as it's condensing within that container. And it's this process that's happening constantly. And so it doesn't look like anything's changing. So once that equilibrium is established, while the liquid level in your container doesn't change, that's because we're at equilibrium and there is things happening in there. And obviously, if we increase the temperature of that liquid, the vapor pressure is going to increase because there'll be more energy taking it into a gas. And yeah, so then your pressure would increase. But what do you have to do with vapor pressure? That's what we want to think about. And we want to think about it with a graph of vapor pressure. So we can use the graph of vapor pressure versus temperature to show how the boiling point of a liquid is related to the vapor pressure. So super important. When the vapor pressure equals the atmospheric pressure, boiling occurs. So you see this line 101.3 kPa, that's our standard pressure at sea level. And you can see where these graphs intersect, those points, that's going to, if you go down, tell you the temperature for its boiling point. And then the ethanoic acid, I don't know why this one is just white, but draw it in there for you. So you can answer questions like these. Which of the following compounds has the highest and lowest boiling point? Highest boiling point would be ethanoic acid, right around here. The lowest boiling point, obviously chloroform over here. What's the boiling point of ethanol at sea level? So we're going to go, okay, here's where they intersect. You go down to the graph, and we can say it's about 78, 79 degrees Celsius. And then finally, what's the vapor pressure of chloroform at 40 degrees Celsius? So you just go up from 40 degrees and over, pretending like you could draw a straight line, and it would be about 50 kilopascals. So really all we need to be able to do is look at these vapor pressure graphs, be able to pull information from them like these questions. It's very simple. The key is when the vapor pressure equals the atmospheric pressure, boiling occurs. So boiling point, when liquid is heated to a temperature at which particles throughout the liquid have enough kinetic energy to vaporize, the liquid begins to boil. That's just like the definition of boiling point. A liquid boils when the vapor pressure of particles within the liquid equals the atmospheric pressure. Okay, boom, we already said that in the last one. Here's something new. Boiling point will vary with altitude. So you can see in these pictures here, we're at 101.3 kPa, so we're at sea level. We're at 20 degrees Celsius. You just notice no boiling is occurring. When we're at sea level, 101.3 kPa, we're at 100 degrees Celsius. Obviously, that's the boiling point of water. So at the boiling point, the vapor pressure equals the atmospheric pressure. And then finally here, I'm at 34 kPa. So that means my pressure has decreased. How do I get my pressure to decrease? So my atmospheric, I'm going to just say atmospheric pressure decreases when you increase the altitude. So you go up higher in a mountain, the vapor pressure, the atmospheric pressure actually decreases. And so here at this pressure, at this atmospheric pressure, we can boil at 70 degrees Celsius. So depending on how high up you are, you can get water to boil at a very low temperature. It's pretty interesting. Phase changes. We should already know these. I'm just going to go through. We know from solid to a liquid is going to be melting. From a liquid to a gas, a couple of terms you could use. That you could use boiling. You could use evaporating. Or the best one, vaporizing. Vaporizing is going to be your best term because the word vapor, it means it originally was a liquid, but now it's turned into a gas. And then a gas to a solid is deposition. Now going the other way, solid to a gas is sublimation. Gas to a liquid is condensation. and liquid to a solid is freezing. So that should be nothing new to you. We did phase changes, I believe, at the very beginning of the year. But now what we're going to do is we know we can do phase changes with temperature, right? That's what we usually see. But we can also change the state by changing the pressure. And a phase diagram actually allows us to see what state we're in depending on both temperature and pressure. So some points on this graph that are important. Point D right here is the triple point. And at this point, which is labeled 0.006 atmospheres and 273.2 Kelvin, is the triple point where all three states of matter occur. So you have a solid, a liquid, and a gas. The critical point is E right here. It indicates the critical temperature and the critical pressure. What do those terms mean? Just some vocabulary terms. The critical temperature is a temperature above which the substance cannot exist in the liquid state. It's too hot, it can only be a gas. Critical pressure is the lowest pressure the substance can exist as a liquid. If the pressure is any lower, then it has to be a solid. Oh, I'm sorry. If the pressure is any higher, it has to be a gas. Yeah. So we can see here that we've also got A, B, and C. So they're the lines. So A is this line here. Maybe I'll do this in a different color. I'll do this purple. A is this line, B is this line, and C is this line. So we need to know what's happening at those lines. So at A, you have both a solid and a gas. So this portion here is a solid, this portion is a gas. So on that line in between them, you have both. So B is going to be both a solid and a liquid, and C would both be a liquid and a gas. So you've got both states occurring at the same time. Okay. Just like at the triple point, you've got all three. Now, let's say, I'm going to clear this. Let's say we didn't know that this was the solid, the liquid, and the gas. Let's say those were gone. How do I figure out what the solid, the liquid, and the gas is? Okay, this might be a little immature, but it will work. Here's a person, boy or girl, because you'll see why in a second. This is a foot, and this is where the gas comes out. So this portion will always be the gas, and then you've got two left, and the colder one, the one to the left, will have to be the solid, and then that would be the liquid. So basically farts, okay, and then you can determine where the solid and the liquid is from that. One other thing, you'll notice that this line for B between solid and liquid bends to the left. If the solid liquid line, I'm going to write this down, liquid line bends to the left, the solid is less dense than the liquid. The opposite obviously is true. Okay, so this line bends to the left, which means the solid is less dense than the liquid. This thing here, let me erase this girl, get rid of this so we can clearly see. This thing is water, okay? So at 273, which is 0 degrees Celsius and 1 atmosphere, that's the solid liquid, the freezing point. Okay, which we know 0 degrees Celsius, 1 atmosphere is the freezing point of water. 373 is 100 degrees Celsius, 1 atmosphere. That's when it's going from a liquid to a gas. That's the boiling point. Okay, so this is water. This is the phase diagram for H2O. And another reason why we know that ice is less dense than water. So that line bends to the left. Okay, that's it for the notes for today. You've got your homework assignment. basically just some vocabulary terms and some phase diagram work. And then there's also a quiz that's associated with this. Of course, if you have any questions, please make sure you ask them in class, put them in the chat. I can answer them for you, and I'll see you back in class.